welcome to this webinar with the title Moving from 2D to 3D with the advanced tools from ibidi. Thank you very much, Peggy, for the introduction. My name is Elias, and I will guide you through this very short, no, not short, but very interesting and basic talk. And I want to start with a quick overview. So first, a short introduction into the field from 2D to 3D, why, and then so on. Then I will show you a very nice collagen matrix for three-dimensional cell culture. Then I will show you some imaging chambers for gels, a very nice chamber for the perfusion of gels. So instead of having a static cultivation, going to a dynamic system. I will also tell you something about chemical gradients in gels. And in the end, I want to give you a short outlook on the ibidi innovations, what you can expect from ibidi in the future. So all this is coming out of the ibidi toolbox. As you can see here, this is the very nicely looking ibidi toolbox. And inside this, as you know, we are a very specialized company for cell culture and microscopy for special assays like the chemotaxis assay, like tube formation assays, for like with our channel slides for the simulation of blood vessels with our pump system, and so on. But also very basic imaging tools like our dishes, our chambered cover slips for live cell imaging, for immunofluorescent staining, and so on and so on. And inside this toolbox, we also have some special chambers or some special technologies, some special products we can use for going from 2D to 3D cell culture. And the main goal for a lot of people at the moment, of course, is moving from a cell monolayer a little bit more towards living tissue or a whole living organism in 3D. Why is that? Because in a living tissue, there's much stronger or much more complex microenvironment, there's more structure, there's more biological relevance, but also the complexity is much higher. At the same time, a cell monolayer is very easy to access with a lot of biochemical tools, with a lot of biochemical assays, which are available very easily. So it is a trade-off between 2D and 3D always. And there's a very easy first step towards this three-dimensional world, and that is hydrogels. With the hydrogel, you are already in the 3D world with your cells embedded inside a hydrogel, completely surrounded by a gel matrix. And this is what I will focus very much today on this hydrogel topic. And the next step with the cells itself forming a three-dimensional structure is, of course, working with spheroids and organoids, which is a little more complex, but very powerful as well, and even more in vivo-like, even more a little more like living tissue in 3D. So first, I want to focus on the hydrogels. And there's a very nice hydrogel system, and that is a very simple system, and that is collagen. Collagen or collagen gel is very easy because instead of having the cells flat on a 2D surface, we can easily mix them with a collagen and create a collagen gel with the cells and have them really in 3D then in this situation. And in the microscopic image, it looks like this, that is a normal adherent cell. Unlike this situation where the cell is very flat and attached on the cell surface, on the flat surface, the cell is completely, in this three-dimensional case, surrounded by the gel matrix, in this case, the collagen gel. And you can nicely see the gel matrix here. You can nicely see the collagen fibers in this phase contrast image. And you can also see that the cells typically have a different morphology in 3D in a cell inside a gel matrix. Usually the morphology inside a 3D gel is more spindle-like, more roundish, which is pretty clear because it's not flat attached to the surface. So collagen gels are very easy to use. That is very simple. It's a very cost-effective system. And one of the biggest advantages is there's a very defined composition. The collagen contains only collagen. There are no growth factors, no other remains from any other proteins or chemokines, which makes the system very flexible. So whatever you want to add into the collagen gel here for your cells, you can add it very easily, very nicely in the form of a chemokine or a special factor or other proteins and so on. And the collagen gel is very nicely suitable for microscopy, especially for fluorescence microscopy. So the optical readout with antibody stainings, with live cell imaging and so on is very, very easy. And it is also very easy to do. And this is just a, yeah, it's not a real protocol. It's just an example how easy it is to create a collagen gel. We have very detailed protocols and instructions for our collagen matrix on the web page. In brief, in general, it is very easy. You just need your cells in your normal culture medium in suspension. You need the collagen. You need water. You need sodium hydroxide to adjust the pH, the final pH. And you can add, if you want, supplements, as I mentioned before. And you need a 10x medium of your choice. And mixing all this together, you end up with a very nice collagen matrix. And this very nice collagen matrix under the microscope can look like this, or usually or will look like this. And this is confocal microscopy of HT1080 cells in green and the collagen fibers in white. And you can nicely see that the collagen is not a rigid structure. Instead, it is very soft and flexible. And in this migration experiment or in this migration assay, you can see that the cells easily can migrate through the gel, can attach through the gel, or can migrate through the gel in 3D, and can easily manipulate and yeah, customize the gel. So that is a very powerful three-dimensional fibrous network, and I always think about the collagen gel matrix like a three-dimensional spider's web. Microscopy is one basic way of analyzing that, and typically people use open wells to image those kinds of cells in 3D gels. And in an open well, you will quickly see that the collagen gel or all kinds of gels will form this gel meniscus here in a normal open well, like in a 96 well plate, with a lot of cells and a lot of gel near the edges and only a few smaller cell number in the center. And this situation is not quite perfect because the cells here will see different conditions than the cells here, because here we have a culture medium which is feeding the cells, which is delivering oxygen and nutrients, and the conditions for those cells here will be different from the conditions of those cells because the distance here is longer and the cell number is higher. So we have a special technology to improve this culturing method and also this imaging method with this what we call well-in-a-well feature or well-in-a-well technology, what we have in this special chamber here. And inside the wells, you can see here very small a step, and in the cut version, you see this step here. And this creates a small 10 microliter well inside this bigger well. And if you fill now your gel matrix exactly with the given volume of 10 microliters inside, you will create this flat meniscus, this flat cell gel meniscus. And you will create the advantage of a very homogeneous cell distribution without this meniscus here. And with the cover slip bottom, you can access microscopy, access fluorescence microscopy very easy. And the conditions, and this is important, of course, conditions for all cells are the same, because the medium in the upper well here, the culture medium, which is giving nutrients and giving oxygen inside the gel layer, all this is done by diffusion. And the conditions are the same now inside here because the diffusion distances are the same. Good. That is, so cells in the gel is one example for that. We can also do something a little different and just seed the cells on top of the gel matrix. And as you can see here in this animation. And if this gel matrix here is a matrigel, and if endothelial cells are seeded on top, then you are in the classical angiogenesis tube formation assay, in which endothelial cells on top of the matrigel will form those characteristic endothelial patterns, which give you some information of the angiogenic potential of the compounds you add or of the cells itself. So that is a very easy way to put cells on top of a gel matrix, but we can also go a step further and combine cells inside the gel and also on top of the gel to create a very easy co-culture system. So in this case, it is 2 cell seeding steps, 1 cell seeding step inside the gel, and the second cell seeding step with a cell suspension on top here, which are falling on top onto this gel surface. And we can even go one step further and sandwich cells in between 2 gel types with different gel types or with different gel concentrations. So there's a lot of possibilities with this gel chamber and with different cell types and different methods, all in 3D based on a hydrogel. And as I mentioned before, there's diffusion taking place between the liquid here, the cell culture medium here, and the cells inside the gel matrix. In this situation, the whole system is static, so it's fully diffusion based. And static means you can add your fresh medium here, you can do medium exchange, you can add compounds to do different things with your cells here, but this is static. And we thought about that for very long, and we thought about how can we make that dynamic. And we came up with an idea to just create a channel over this gel matrix, over this well with the gel matrix. And this is, again, here this step, so we can easily create a flat gel surface. And in reality, in the chamber, in the microsite 3D perfusion, it looks like this, that this is the well. And here we have small channels which are connecting the wells and which are giving access to this perfusion-based dynamic system. And with this perfusion-based dynamic system, we can easily connect a pump system like our ibidi pump system, and we can do long-term perfusion. And with this long-term perfusion, we can deliver oxygen, nutrients, and so on to the cells inside the gel. And we can later on collect the supernatant from this perfusion in the fluidic unit here. And we can also do microscopy from underneath, of course, because it's also imaging based. The outlook is also the readout is also imaging based. At the same time, there's no shear stress, and this is scientifically important because the cells here are embedded inside a three-dimensional gel, a hydrogel, which is from the flow resistance very, very high. So the flow will be in this gel-free area only, the perfusion, and the cells which are embedded inside the gel will not see any mechanical flow, will not feel any mechanical force, and will not see any shear stress. That is especially important in this area. So this is just a delivery method for fresh medium and for longer cultures. And with longer cultures, I mean in the static way, we are typically in the range of hours to days for those systems, and here we are easily days to weeks with those systems. The next important technology for three-dimensional culture is creating chemical gradients in the gel matrices. And we have a special chamber, what we call microslide chemotaxis, with a system like this, in which we have a very small channel. And this very small channel is filled with gel matrix and cells inside. And this small channel is connected on both sides to large reservoirs. And those large reservoirs here can be filled with two different liquids. So one is a normal culture medium, normal cell culture medium, and the other one can be the same culture medium, but with a chemoattractant, or with a special chemokine, or with a special chemical. And if there's a concentration difference between this side and this side, then the system by itself creates a chemical gradient, a linear gradient across this gel matrix, which can be felt by the cells, which can polarize the cells, and the cells then, the polarized cells then can migrate through the gel in 3D towards the stimulus, towards the chemoattractant. And this works for all hydrogels like collagen, what I showed you before, like matrigel, fast or slowly migrating cells. The concentration gradients are very stable, 24 hours, 48 hours, no problem. And the microscopy access is really excellent, is perfect, because in a system like this, we need microscopy access to see the cells moving. And in this case here, you can see the cells nicely moving through a gel matrix. This is, again, a collagen matrix, which you can see in the background. The cells are moving inside this. And this area here is the normal, or the pure time-lapse movie in phase contrast. And on this side here, we have analyzed that, or we have automatically tracked that with our machine learning algorithm powered by artificial intelligence, which is automatically detecting the cells and the cell bodies. And with this, you can easily automatically follow the cells and determine the positions where the cells are at which time point to measure the migration and to measure the chemotaxis effect. So that is chemical gradients in hydrogels, and that is the story for cells in gels, in hydrogels. And the next step is moving to spheroids and organoids. And with that, I'm already in the outlook part of my little talk here. So when we talk about imaging spheroids and organoids, and as you know, ibidi is very focused on imaging. So we have done a lot of spheroids, organoids work in our lab, and we used all those different plates for imaging those spheroids. As you probably know, there are round bottom plates, there are flat bottom plates, especially made for imaging. There are special geometries for spheroids for imaging them or for creating them. But we were never really satisfied with some points, especially in round bottom plates. The imaging quality is bad because of this, again, meniscus or this round bottom here. It is much better in those cases. But we also were not very satisfied with localization because also even in those round bottom plates, and especially in this situation, you never know exactly where the spheroid is. Even in those cases, depending on the size, the spheroids are never completely exactly on the position you want them to have, or you expect them the next time you put it on the microscope or you want to do imaging. Additionally, we were also not satisfied with the environment. And with environment here, I mean the capability of a medium exchange. So having fresh medium put in without changing the position, maybe apply a flow, apply a perfusion, apply shear stress to the spheroids. All this is very, very bad. It's almost impossible in those systems. So we are at the moment working on a special solution, which is based on our passivated bioinert surface, which is a very powerful surface passivation. So cells cannot attach on this bioinert surface because proteins also cannot attach. And if we, with our micro patterning technology, if we create a small spot with extracellular matrix, so with adhesion proteins or with adhesion motifs, we can easily collect or catch spheroids on top of a surface like this. And that works very nicely. That works very nicely with spheroids we can seed directly on those surfaces, or even with cell suspension. So if we put on cell suspension, and I will show you that in the quick video later on, you can see that the cells all gather on those adhesive spots because they cannot attach here. And with that, we have very defined positions. We can apply shear stress or perfusion and flow, deliver nutrients, oxygen, compounds, and so on. Again, collect the supernatant. We can harvest the spheroids, and we have access to high resolution microscopy. As you can see here, the confocal microscopy is very easily possible because there's no restriction. The bioinert surface is perfectly compatible with all kinds of fluorescence microscopy. And as you can see here, we can create very defined spheroids on very defined spots, without additional effort. And overall, that is what we are aiming for: the perfect imaging quality, perfect localization, and the perfect environment. This will be available soon. This is why I have this in the Outlook only. And this is the video I just talked about, I just promised to you. So as you can see here, we do have our adhesive spots. And over time, the single cells we just seeded here will collect there, will attach to each other, and will form those spheroids. So this is the application in which we seeded single cells, but we can also seed a suspension of spheroids on those spots, which are created by a different technique, by a hanging drop method, or by any other spheroid creation method. And this is what we have done in the next slide here, in the next experiment. In this case, we have seeded single spheroids, which were made by a hanging drop technique, onto those spots. And this is why there's not always a spheroid here, because we used a slightly low concentration of spheroids, but that's not the problem here. The idea of this was to connect it to a pump system, to our pump system, and perform a 14 days constant medium perfusion. And in this row, you can see the images of the spheroids after 14 days in under static conditions with daily medium exchange. And in this row here, you can see how the spheroids evolved or grew under constant medium perfusion, and you can clearly see after a couple of days a huge difference because of the oxygen and nutrient supply, and you can see that the spheroids are forming very compact, and it just creates a very easy and powerful method to have a spheroid culture on defined spots in a highly defined environment, under perfusion or under slight perfusion or under static conditions. And with that, I want to conclude almost. My last slide here is a motivational slide. So my take-home message is get started, because it is easier than you think to go from 2D to 3D. I showed you the collagen gel matrix. I showed you some ideas to use those chambers for the gel cell mix, for cells embedded in hydrogels under static conditions, with gradients, or under perfusion conditions, under dynamic conditions with the pump system, for instance. We do have, and this is my last minute, we do have free samples of our labware. We have demo systems for the pump system, and we have an excellent technical support in Munich. So you can easily call us or write us an email, and we will help you with all the questions you might have. And with that, I would like to thank you for your attention. And now we are open for questions, Peggy, I think, right?
That's absolutely right. And there were actually quite a lot of questions filing in. So I assume there are a lot of people who found that talk interesting. Let's start with Franziska. I believe she put in a question quite early, but I think it's already answered, because she asked if what's the best option to grow 3D spheroids without a matrix and to make microfluidics. This is what you showed at the end.
Exactly. With this technique here, or with this technology, we are not really focusing on the creation of the spheroids. This will be possible as well, but we are more focusing on the assay itself, or on the microscopy.
Right. Yeah. So look out for those solutions. We are going to launch beginning next year, probably. Next one, Magda. Magda is asking, what's the height of the gel in the microslide angiogenesis?
And that is exactly 0.8 millimeters. So it's 800 micrometers in height. This height here is 800 micrometers. 0.8 millimeters.
So Magda, I think that answered your question. And we have Kilian is using the microplate angiogenesis. And he has some trouble with high adherence of the cells at the bottom while doing 3D, I guess. So do we have any recommendations?
Yeah, that is an interesting thing, because if those cells here embedded inside the 3D gel like to attach to the bottom more, or to the flat surface more than to the gel, then you will quickly see exactly this. You will see this and gel on top, and have some kind of a 2.5D situation. What is yeah, it's it's described this way, then 2.5. You can try different things. You can try to I don't have a short answer. It is a lot cell type specific. Some cell types like just hard surfaces, and then they whenever they find a hard surface, they attach there. Because if this whole well is filled with a collagen gel, then it is like a collagen coating on the surface as well. So it is very cell type specific, but you might be able to pre-coat the wells with something I don't have right now in my mind to hinder the cells to attach to the surface. Additionally, one thing I like to mention is during the polymerization phase or during the gel formation phase, the cells are like in a liquid and will sink down. And if you optimize the protocol and minimize the time for formation of the gel, the cells do not have much time to sink down.
So that it polymerizes quicker, I believe.
Yeah, if you polymerize it quicker, or if you some people also during the polymerization phase flip the whole thing upside down. So it is every 5 minutes they do a upside down turn. So the cells will sink in a certain direction, and then you flip it, then they sink again. So during the gel is forming, you keep them in suspension, so to say.
Even the plate, the
Yeah, even the plate.
Okay.
Yeah, even
it's not spilling out. That's interesting.
No.
Cool.
This is too small. Wait a minute.
No. Okay, Kilian, I hope that answered your question because there's so many. I believe we should move on. So just turn around the plate. And yeah, all the steps that Elias mentioned. Magda has another question. She's using the microslide chemotaxis and has trouble of the gel spilling out into the reservoirs, even though she follows the instructions of the product.
Yeah, for that I think we do a one-to-one talk. There's ways to optimize that.
Magda,
there's ways to optimize. Yeah.
Could you please send an email to techsupport@ibidi.de? You will probably end up with me or one of my colleagues from the technical supports team, and we can give you some advice. I think otherwise it's probably too much information at this point here. Thank you. Tatjana asks, we talked about collagen matrix, and can you recommend any other attachment factors?
The collagen itself is only collagen. Yeah, this is true. If you want to increase the attachment inside the collagen matrix, you can easily add other collagens, not only collagen type 1, but also collagen type 4, for example. You can easily add laminin into the collagen mix to laminin or ornithine to go a little into the direction of matrigel. So basically, you can mix up all those adhesion proteins inside a collagen gel matrix. There's a lot of publications out there, so you can just see what is published and just copy it.
It's always a good idea.
Yeah, I mean, let's be honest.
Okay, thank you. I hope that answered your question, Tatjana. Carrie is asking if we have any animal-free alternative or protocols for collagen hydrogels.
Not at the moment, but there are animal-free hydrogels around on the market. So either from plants, matrices from plants, hydrogels from plants, or pure chemical hydrogels. So there's a lot of gels outside, which you can all, of course, use to embed the cells. But they need, of course, to fulfill some they need to do some things. They need to be somehow cell-friendly, and for most cells, you need the adhesion inside the gel matrix. Otherwise, they will not attach inside the gel matrix and die. But there's a lot of publications also for this around with other gel types,
Yep.
hydrogel types.
We cannot help here at the moment, but we'll see what the future brings. So Moning has a very interesting question. He asks, how long can a 3D gel culture be maintained? Meaning the cells continue to divide, they eat the gel, probably decompose the gel in some way. Does it have any effect on the gel? Are the holes filled with medium or ECM made by the cells?
That is a very good question. It very much depends on the gel type and also on the cell type. So there's no general answer. I cannot say that this is working for 2 days and after 5 days everything is dead. So this very much depends on the assay. There are cells which digest the gel, the cell matrix, the gel matrix, of course. As you've seen in the video, the gel is changed over time by those fibrosarcoma cells, and because the cell number is also changing over time, some cells are digesting the collagen, some cells are not. It very much depends on the combination of cell type and gel. And the gel itself is not like a solid block of gel. The gel is, as you can see in the video here, the cell is 99% medium, and only the fibers are the gel matrix. Those solid fibers are is the construct of the gel.
Great.
So if the gel is gone, the rest is medium. Yes, it's culture medium.
Thank you. Then Tatjana is asking, she sees that our tools are small cell yield systems, and she's looking for more cells to do Western blot with. Any ideas? For bigger holders.
For bigger. Yeah, bigger vessels have more capacity for more gel and more cells. We very much focus on the imaging output, but as an idea, our dishes, what I have shown you here, I mean, I'm not prepared for this. Our dishes do have an inner, a large inner, imaging area, in which it's 21 or 22 millimeters in diameter and 1 millimeter in height. And you can, for this kind of application, you can also use that to use this well in a well technique and to have a really huge well in a well with a lot of cells and a lot of gel. 800 let's say, how big is 400? 400 microliters of gel then instead of 10.
But would the cells survive in that?
Yeah, totally.
Okay,
of course.
So there's enough medium diffusion. Okay.
Yes.
Mm-hmm.
Yes.
Now I have to make a shout out to all the people watching here, because they're actually helping each other out when they have questions. Because Alexandre asked if for a protocol on doing stainings or sections of spheroids. And I think Tatjana answered him. And so contact Tatjana. She put her email address into the chat box if you want to know an answer for that, because I believe we don't have one. So thanks for that, Tatjana. Then Julia Thorne asked what tool we used to track the single cells for the chemotaxis assay, and Magda already knew. But only half. That was half true, Magda. We have an ImageJ plugin where you can manually track those cells when you do chemotaxis assays. So you go from image to image to image to follow 40 to 100 cells, which takes a lot of time. The movie that you saw was done with Fast Track AI. This is also something we offer in cooperation with another company called Labs. And this is an automated system. So you upload your images, the time lapses you performed for 24 hours, 48 hours, and then it analyzes it within 5 minutes to 2 hours, depending on how many images it is. You can test it for free. If you go to our website and search for Fast Track Chemotaxis, you can register. It's an online platform. You upload your data and then get the results. So if you're interested in that, you can test that. But Magda, thank you very much. You definitely put some energy into working with the chemotaxis slide. Philippe was also thanking Tatiana for the protocol. Here we have another question from Boning. Is collagen 1 gel suitable for culturing neurons? He tried 2 milligram per milliliter and it did not work.
It did not work. I am not a huge neuronal expert, so I cannot answer that at the moment. I think the neuronal adhesion is not really satisfied by the collagen itself. I think you need to combine that maybe with other adhesion motifs. So I don't know at the I don't know at the moment. I can only refer to literature if there's something already published, maybe what you can use.
Okay, thanks. There was more information. They thought that's probably because the collagen 1 is not really brain-like environment. Maybe this could also be a factor.
Yeah, and it's very, yeah, let's say pure.
Mm-hmm.
It's very
So
pure.
maybe matrigel could be, but literature should know best.
Literature knows best in this case. I don't want to go in to get into any trouble.
We know a lot, but we don't know everything. Sorry.
Yeah.
But I have to get back to Tatiana because Tatiana asked about the possibility to harvest the cells from 3D gels, I believe, for Western blot, but with shear stress. So channel slides, I assume.
So in principle, it is very easy to remove the gel if you have mechanical access. So you can, yeah, with some mechanical force, you can pipette the gel out again. You can also use the enzyme which is digesting collagen, collagenase. Or we also have a recommended collagenase product recommended in the instructions to completely dissolve or digest the collagen matrix, and then the cells are left over. That can be an option.
So I hope I got your question right this time, Tatiana. And in the meantime, we can go to Nastaran. They're asking if we try to transfect organoids using a transfection reagent. And what would be the most efficient one?
No, we have not tried that.
Sorry.
No.
All right. So if there are no more questions, I would like to say thank you very much for your attention. And I hope you enjoyed this webinar. It was nice having you, discuss with you, and wish you a nice evening or morning, depending on what end of the world you're listening from.
Yeah. Bye-bye, everyone.
So thank you very much. Bye-bye.